So here we have a nuclear power plant. The nuclear power plant has an electrical power output of 1,000, what's MW? Megawatt. Okay, so on this diagram, all heat engines can be diagrammed like this. They operate off of heat. So you have a hot reservoir, you have a cold reservoir. What does the heat energy do? Heat energy flows into the engine, which in this case is the power plant. Some of that comes out as useful work, which we're going to call power output. You know, if you're talking about the power output of this plant, you know, that's how much usefulness you're getting from it. And then the rest of the energy gets dumped to the cold reservoir. Hey, where do they always build nuclear power plants? Near the ocean or a giant lake, perhaps. Do they have next to lakes? Perhaps. Ocean is good because why is the ocean good? You can dump massive amounts of heat energy into it, and it's so big it just absorbs it. You know, it's called a heat reservoir. Okay, so we have power coming in from the hot. We have power output, and then power being dumped to the cold, which is basically like the cold reservoir is almost like the trash can. It's like a trash can for the excess energy that wasn't used. Okay, so our power output is 1,000 megawatts. And just keep in mind, what's mega? Mega means what? 10 to the 6. Mega is a million. Okay, they tell us that the efficiency of this power plant is 33%, which is 0.33. Okay, so the first thing I want to do, let's figure out what's power from the hot, what's power to the cold. So what's the efficiency equation? Efficiency is going to be this divided by this. Does that make sense? So it's going to be power output divided by power from the hot. Okay, so rearrange this. Power from the hot, it must be power output over the efficiency. The power output is 1,000 megawatts. The efficiency is 1/3. So the power from the hot must be 3,000 megawatts. You guys get it? 3,000 megawatts. So that's 1/3, right? If 3,000 megawatts come in and 1,000 of it gets used for something useful, what would be the efficiency? 1/3, right? So how much power gets dumped to the cold? 2,000. Okay? And that's what we need, guys. To answer this question, this is what we need right here. 2,000 megawatts. And by the way, what is 2,000 megawatts? Well, so mega is 10 to the 6. What's a watt? A watt is what? A joule per second. So this right here is actually 2 times 10 to the 9th joules per second. Okay? The energy being dumped to the cold is 2 times 10 to the 9th joules per second. Now, here's the question. If excess energy is carried away from the plant by a river, so this cold reservoir down here, I'm just going to erase it. What is this cold reservoir? It's a river. Okay, so we got this river. There's a river like this, and the water in the river is flowing by at a rate of 10 to the 6 kilograms per second. Okay? Every second, how much water flows by? Every second, how much water goes by? 10 to the 6 kilograms, right? So here's what you do. For this problem, we're going to focus on what? How much time? Focus on 1 second. How much, what's the mass of the water that flows by in 1 second? In 1 second, how much water flows past? 10 to the 6, right? 1 times 10 to the 6, because they tell it it's 10 to the 6 kilograms per second going past the power plant, right? How much heat energy, because look, what's the power plant doing? The power plant is dumping heat energy into the river. How much heat energy gets dumped into the river in 1 second? It's right here. How much heat energy gets dumped into the river in 1 second? 2 times 10 to the 9th joules, right? So now we got Q. Now, there's something else I would, there's something else that you have to know to answer this question. What do you have to know about water that's not mentioned? The specific heat. The specific heat of water is 4,186 joules per kilogram degree Celsius. And the equation that relates this all is heat equals M times specific heat times change of temperature. Q equals MC delta T. So the change in temperature of the water is going to be Q over MC. The Q is 2 times 10 to the 9th joules. The M is 10 to the 6 kilograms. And then the specific heat is 4,186 joules per kilogram degree Celsius. So you punch that into your calculator and you get a delta T equal to about 0.48. Ba-bam.